So I welcome you to Aerospace Structures 1. We're going to cover the course overview for this class. First, let me introduce myself. I'm Vinay Goyal. I have a bachelor's in mechanical engineering from the University of Puerto Rico, Maya West campus. Actually, I grew up in Puerto Rico, so my first language is Spanish. And then I've lived here in the United States for a long time. I have a PhD in aerospace and ocean engineering at Virginia Tech in 2002. And my specialty was really the design and evaluation of aircraft applications, especially those made of composite materials. The experience I have is structural systems, aerospace structures, composite metallic designs, bolted bonded joints, dynamics, and failure modes, such as fracture, fatigue, buckling, and so forth. My hobbies are basketball, chess, hiking, beach, and I'm a foodie. I love food. But in general, I'm passionate about aerospace engineering. I really enjoy the designs of launch vehicles, spacecraft, and aircraft, and even designs of other components that may not have to do with aerospace. I just find it fascinating, particularly because it's kind of fun to work in the design of something, and you don't know if the design is going to work. That uncertainty of verifying a design and basically trying to figure out whether the design is going to survive a structural test that could be exposing failure modes in the structure that could be quite concerning. And so you don't know if the test is going to pass or not. And so that really increases the excitement that I have for this field. And then the second thing I really enjoy, and it sounds very strange, but I do enjoy anomalies that occur, because when they occur in flight, it's an opportunity for me to learn, and it's an opportunity to learn from the failures that we have seen. What are the course objectives? What do we have in mind? Is what we want to do is gain a fundamental understanding of launch vehicle, spacecraft vehicle, and aircraft vehicle structural design considerations. We also want to understand the types of failure modes that could drive the designs. We also want to cover lessons learned from these failures and how to conduct a failure investigation, which I think is very important when you're dealing with anomalies. We're also going to cover material selection for various applications and the limitations of those materials to these three applications: launch vehicles, spacecraft, and aircraft vehicles. We're also going to analyze the external and internal loads in these aerospace structures. And then we're going to look at the requirements that exist from the FAA, AIAA, NASA, and other organizations, so you can understand what are those requirements that drive the designs in general. And as we do so, I think it's important that you start reviewing statics of materials, which can be an important subject, and also mechanics of materials. Those two courses can be quite valuable in this course as well. The next thing that we're going to talk about is the course materials. The text and references for this course will all be provided to you. I'll provide you all the course materials in PowerPoint in the form of briefing packages, paper publications, NASA and FAA publications. The primary textbook of this course is the one I wrote with my brother. It's called Analysis of Aerospace Structures. and it's the first edition. Um, this edition here will cover primarily aircraft design, but it can also cover, can be extended to other applications. The course will cover topics that are not included in this book, such as launch vehicles, spacecraft vehicles, and potential lessons learned from failure. Um, we will cover some FAA requirements in this book, but not all of them. For example, AIAA and NASA requirements may not be covered in this book. What we're going to be discussing now is the additional recommended books. Spacecraft and Structures and Mechanisms is a book I recommend if you're going to work in the spacecraft world. I'll be covering topics from that book as well. And I also recommend getting hold of other books if you're going to work on aircraft designs. It's called the Aircraft Structures for Engineering Students. That's another book I recommend if you can get it from the library or get a used copy. But I will primarily using my book, so this is not a requirement. If you want to see how others will approach a subject, then it's worth it. Aircraft Structures by Peary. We also have airframe structural design, practical design information, and data on aircraft structures. This book is also recommended for you to purchase or to borrow because it could be helpful in your career if this is what you happen to pursue. You also have the book Airframe Stress Analysis and Sizing. Again, another great book. So all these books are recommended, not required. I'll be covering a lot of these topics through these course materials. So what is the motivation for this course? The motivation is that aircraft, spacecraft, and launch vehicles need to be designed to be lightweight, low cost, reliable, and robust to be able to meet some mission requirements. And so it's important to understand that what this course is doing is giving you that background. And what makes aerospace structure so complicated compared to, say, a ground system like a building is that an aircraft, spacecraft, and launch vehicles contain a lot of pieces coming together to perform a function that's not very simple. Secondly, the primary difficulty with these designs that they need to be low weight. They have to be lightweight because we're flying them. And not just that, they need to be robust. They may contain, they could have occupants in them, for example, or the mission that they're going to fly, perhaps that mission costs billions of dollars, as an example. So the topics covered in this course are intended to be an application of the strength of materials courses you may have taken, and then applying those concepts to the analysis and design of an aircraft and launch vehicles. Here's an example of an aircraft finite element model. A finite element model is a mathematical representation of the structure, and it allows you to solve for specific variables of interest that allows you to then evaluate the design to ensure that is robust enough to operate in flight. On the right hand side, I have a rocket model. It's a finite element model as well. In this case, you have a solid rocket motor where the gray region corresponds to the solid rocket propellant. In these two scenarios, these finite element models were developed to try to fundamentally understand the designs during operation. Boeing 787. In this example, there was wing damage that grounded the Boeing new composite 787 Dreamliner. It occurred when the stresses on the wings was well below the loads the wings could take. Damage occurred on either side of the wing body joint. So here in this region, Um, and you know, in this area, the structural flaw in the Boeing design was found during the ground test that bent the wing upwards. So one of the testing that's done is to apply loading to these wings, and what we do is we apply loading to the wing and we bend it upwards, and we can bend it several feet up. And the purpose of that test is to verify the integrity, the design integrity of that wing. And the stresses at the end of the long rods that stiffen the upper wing skin panels cause the composites to delaminate. And damage did occur at the end of each of the 17 long stiffening rods, which we typically call stringers. And on each wing's upper skin, there was some amount of damage. And testing, um, the testing was supposed to go to ultimate load levels. I'll discuss ultimate load levels later, but the bottom line is that it occurred very close to the loads that it will have seen in flight, the maximum loads expected in service. And so for that reason, these design had to be revisited. The sources given here at the bottom, but the question then becomes, what failed here? Why was there an issue with the testing? Well, the bottom line is that testing is important for a reason. Testing allows you to gain an understanding of the failure modes of the structure. Not only that, it helps validate the analysis. If you put all your stakes in analysis, there's a potential that your analysis was insufficient or was incorrect. Testing allows you to not only verify the analysis, it helps you verify the design in the analysis as well. And so you can see how this caused significant amount of delays in the Boeing 787 Dreamliner program. Another example is the motivation behind why we're studying this. And it's not that I'm going to go in this course and trying to solve these problems, is to show you that structural failures do occur and that therefore motivates the need for learning some of this material. In 2015, the Falcon 9 V1.1 design carrying the Dragon CRS-7 mission failed towards the end of stage 1 burn. A strut holding an internal helium pressurization tank broke during second stage initialization at T plus 139 seconds at 45 kilometers altitude. The resulting failure of this strut caused the second stage to blow apart. And this scenario here is described in the source here at the bottom. You can go to that link and study this more. But there's also a second anomaly that occurred. It was a giant fireball during the launch pad, on the launch pad, when the vehicle was on the launch pad, preparing from some testing. And the helium being loaded into the rocket caused a failure. And the engineers at SpaceX zeroed in into the composite overwrap pressure vessels. The COPVs is a topic I cover in part 2 of this course, the second part of this course. And so there's also linked here at the bottom for you to study more. The bottom line is that aerospace structural design allows you to understand the failure modes of the system. It allows you to learn how to prevent these failures from happening. But even when you try your best, it doesn't mean that when you try your best, failures will be precluded. There's still the potential for failures to occur because failures are complex in nature, and it can be missed by analysis approaches. Moving forward, we have the spacecraft, the James Webb Telescope, which is an amazing piece of science. This is going to be unprecedented. It's going to be able to see farther than we could see with the Hubble's telescope. And you can see here the backbone of the structure is highly complex. And it almost needs to be motionless so that the mirrors that are attached to this backbone can see far into deep space. This structure is designed to provide unprecedented thermal stability performance, meaning when I'm subjecting this James Webb telescope at temperatures potentially colder than minus 400 degrees F in space, we need to make sure that the backbone of the structure be steady up to 32 nanometers or smaller than the human hair. This backplane is actually part of what we call the telescope structure, and it includes the secondary mirror support structure. It includes the deployable towel structure. And, you know, all of this has to work well together. And it's no surprise that the James Webb Telescope has experienced delays because this is a very ambitious and very complex program. The course outline is as follows. We're going to go through the overall design process for aircraft, spacecraft, and launch vehicles, the stress-strain constitutive law, and finite elements. So we're going to cover some fundamental aspects that are important to this class. Structural failure modes. We're going to go through an overview of aircraft, spacecraft, and launch vehicle components and their design drivers. And we're going to connect these two together. We'll then move on to material selection and testing for aerospace structures. And then we're going to cover aerospace structures, load, sizing, and design. And that's going to cover aircraft, spacecraft, and so forth. Then we're going to move to FAA, AIAA, and NASA regulations that contain analysis, qualification, and acceptance test requirements. And then from there, we'll move to lessons learned from structural failures and failure investigations. Then I'll move on to aerospace structural mechanisms such as clamp bands, bearings, and things like that. We'll then have some case studies from industry and perhaps make progress there. And so today we'll be covering aerospace structure 1, aerospace systems engineering, and I pulled from a variety of resources here, as you can see. And why we need to cover that is because when you design an aerospace system, it is complicated and it does involve and draws from a lot of different disciplines. You have aerodynamics, you have propulsion, you have thermal, you have dynamics, you have structures, you have manufacturing, quality and control. And all these systems become quite important in the design of the aircraft or launch vehicle or spacecraft. And all these disciplines have to work very coherently together to accomplish the mission design. And while this course is about how to deal with the aerospace structural designs, the reason I'm bringing this up is because it becomes very important that the structures team can interact well with the other disciplines in order to accomplish the mission that's planned. Many subdisciplines do exist within each of these disciplines. As an example, in the structural design discipline, you may have non-destructive evaluation, which is basically methodology to inspect hardware for flaws. You may have to involve material scientists, CAD designers, the test team, the team that's going to be doing the testing, and the technicians that go along with them. stress analysts that will be performing the analyses to verify the designs, and B, basically help you prepare for the testing. And that's a topic we've been bringing up because if I make up a design that's not easy to manufacture, or if I come up with a design that's very difficult to test, or I'm using a design that has not very good materials that could be corrosion sensitive, or if I have a design that cannot be inspected, then that could be an issue in trying to accomplish the mission objectives. And so it's important for us to understand that the interactions of one individual can affect other individuals, and the interaction from other individuals towards you is equally important. And every member in a design team working on the design of our aerospace application, that is, every person in that team is important for this to succeed. And you need coordination across all these disciplines, and we need to make sure that the disciplines are talking to each other to enable success of the aerospace system in question. And so the combination of elements that function together to produce the capability required to meet that particular need is what I'm calling the aerospace system. And the elements that include that are the hardware, the software, the equipment, the facilities, the personnel, the processes, and procedures needed for this purpose. All these need to work together well across disciplines in order to be able to succeed from the point of concept design all the way to production and operational phase. So what is systems engineering? Is a disciplined approach for the definition, implementation, integration, and operation of a system. And the emphasis is on achieving a functional, physical, and operational performance requirements in the intended use environments over its planned life within a cost and schedule constraint. You don't have infinite amount of time and money to make the product work. You may have some limitations. And so you need to have a disciplined approach. You have to make sure you have all the stakeholders that are going to be helping in place. And you have to make sure that the team is working well together. So the systems engineering really includes the engineering processes and technical management processes that consider the interface relationships across all elements of the system and other systems, or as part of the larger system. And so systems engineering, sounds like a very it's like a jargon, but it's not. It is what holds the whole thing together. And systems engineering relies a lot on the project management. And that's a process of planning, applying, and controlling the use of funds, personnel, and physical resources to achieve a specific result. If I don't have good project management, the project is likely going to be a failure. And I have to have some planning. I have to have controlled use of funds. I have to make sure that the efficiency that's embedded into the planning of the project is optimal. I have to make sure that the teams are talking to each other. Otherwise, the project will be a failure. And so then also the systems engineering needs to make sure that the interfaces between the disciplines are working well and they're communicating. For example, if the structural team is designing an aircraft or launch vehicle component to 150 degrees Fahrenheit, but the thermal team worked with the fluid mechanics team and determined that the temperatures that the system is going to see is closer to 300 degrees F. Well, if these teams are not communicating, the structures team will complete their design and the thermal team will have not communicated to the vehicle structures team that there is an issue indeed, for example, that should be looked at again. And so all these disciplines have to constantly talk to each other to ensure that the requirements from one discipline to another are getting flowed down properly so that their interfaces are smooth and that we can make progress in the designs. So the systems engineering is a robust approach to the design and creation of our operational systems. And the approach in systems engineering relies on several key elements: identification and quantification of system goals, develop alternative system design concepts, performance of design trades, selection and implementation of the best design. So you may have many different designs, but if you need to down select the best design, that's what you want to do. Verify that the design is properly built and integrated, and then perform an assessment of how well the system meets the goals. You do want to have alternative concepts for the design, because if you only put your eggs in one basket on one particular design, there's a potential that if that design does not pan out, you're left with nothing. So it's important to entertain multiple design concepts that are strong, and then you do the design trades that allow you to down select to the best concepts, which then you can then mature further. The approach here is quite iterative. You have to iterate on the requirements, the design details, the verification plans, the cost, and performance estimates. And when I say requirements, as an example, if I want to launch a vehicle that needs a specific impulse of some kind, say I need 350 ISP for my launch vehicle design. That's a requirement that the system has to meet. If I have an aircraft that I'm going to design, and the aircraft design has to fly from here to a country that's, for example, in Africa, nonstop, that's a requirement. I have to make sure the aircraft is capable of doing so. So those are the kinds of requirements that need to be put in place to really understand whether your design can meet those requirements. Those are functional requirements, performance requirements that need to be met. Not to be confused with regulatory requirements like from the FAA, making sure that requirements that the system meets FAA requirements different from functional requirements. You also may need to iterate on the design details and the cost and performance estimates. These things may be invalidated by new findings during the process of the design. So why do we need systems engineering? The systems of pieces are built by different subsystem groups and may not properly perform system functions. And so at those interfaces, I need smoothness. I need to know that these subsystems are working well together. Now, I'm not just talking about the disciplines, but I'm talking about the pieces that are being built. For example, if I had the team that works on the engines, and I have the teams that works on the rudder system, and I have another team that works on the nose, I may have a multidisciplinary approach for each of those subsystems, but I need to make sure those subsystems can come well together as well. So not only I need to make sure that each subsystem is working well together as a team, I also need to make sure that the interfaces where the subsystems come together, that we don't have an issue there at those interfaces. The problem really emerges typically when subsystems are designed independently and are not well integrated. Why that happens is because managers will focus in their areas of expertise, or in their subsystems arena, and forget how their subsystem has to work well with others. They may develop systems that are not even usable by the other subsystems. So without a clear understanding of what must be done for each subsystem, the development team runs the risk of inconsistent designs, conflicting interfaces, and even duplication of efforts. This also can cost money, cause schedule delays, and also cause performance problems. So factors contributing to program failure and significant cost overruns are systems engineering factors. Inadequate requirements that are not flowed down properly, poor systems engineering processes, inadequate heritage design analysis in early phases. And what I mean with heritage is that when you're designing a product, you may have an early version of that product that has been successful. So using those heritage design analysis practices and not using them properly could be a problem. Inadequate system level risk management, meaning say I have a risk in a particular subsystem and that risk can affect other systems. Not having a system level risk that can be visually seen by other groups could be a problem as well. So the systems engineering needs to provide a systematic, disciplined approach to defining the problem for each member of the team and what must be done for the success. And so I encourage you to look at the source here at the bottom. So it is also a necessary part of every space project. The function of systems engineering is to guide the engineering of complex systems. Most space projects struggle keeping their cost and schedule plans down. And systems engineering helps you reduce those risks. It's just the complexity of space systems that makes this so difficult to attain. You can look at almost every space system, and the James Webb Telescope has, for example, been delayed over and over and over. Systems engineering decomposes projects in both the product and time domain, and then breaks up the problem into smaller pieces that are easier to solve. And so this is the foundation of systems engineering, is that building block approach that I'll be covering later on, but breaking up the problem into small pieces so we can then attack the problem in a way that's doable. Here's an example of $5 billion spy satellite that's behind schedule and expected cost went over 13 billion over budget. The optical system of this future imagery architecture was canceled in 2005 after 6 years and spending over more than $4 billion. And why is that? Why is that? There was a failure in how systems engineering was applied. There was a decline in the expertise in that arena. The science and art of managing complex engineering projects to weigh risks, gauge feasibility, test components, and ensure that pieces came together was a miserable failure. And you can look at the article there to look at that deeper. So systems engineering may not always prevent overruns. See JWT, the James Webb Telescope. It's a large, complex project with many systems integrated. So a systems engineering may not always prevent overruns, but bad systems engineering can be equally bad as not having one. So it's important to understand that the whole point of systems engineering is to stay on schedule, be efficient, and bring teams together working very closely together in a well-oiled machine. If I don't have that, then you may not be even profitable down the road. And you may not be able to even meet program requirements and the final product will be a failure. So it is important to understand that nobody is asking a systems engineer to foresee all possible issues that could happen during the life of the program that may not allow you to fly when you're done. But it's important that the systems engineering team that's put in place works very hard with the team in place to make sure that we have a well-oiled machine, that any risks that are coming up are getting mitigated and worked on to ensure that we have a product that's more likely to succeed. Nobody can guarantee that product will succeed, but what you want to do is put the pieces together to increase the likelihood of success. So why systems engineering work may not work? You have unrealistic budgets. You have unrealistic schedules. You have a technology that's so ambitious that you're pushing the state of the art with a significant R&D investment. And so you may not have the technology readiness level that's required. And that may not have been completely vetted. And what is a technology readiness level? It's a method for estimating the maturity of technologies during the program. And this was really developed by NASA. And the idea here is to really understand how competent this design is going to really be and how mature it is to where it needs to go. So TRL1, for example, is basic technology research. And if I say, okay, in 2 months, I'm proposing a concept design that has never been investigated before, if it's a TRL1, basic technology research, you don't even know if it's just going to work out. So any schedule or budget amounts they put on paper may not be even may not be able to achieve those budgets and schedules. Then you have TRL2, which is research to prove feasibility, and that's also TRL3. Then you can move TRL4, which is technology demonstration. And then you can go to more mature systems such as system test, launch, and operations. And so it's really important to understand how ambitious you are compared to what your schedule looks like and your budget impacts are. Nobody's telling you not to be ambitious. You can be ambitious with the technology, but then make sure there's room to develop the technology with R&D, research and development. Lack of oversight. So perhaps the FAA or the NASA or whatever organization may not be overseeing what's going on. So when the product are close to completion, we have an issue where the product is not meeting the regulations that need to be put in place for safely operating the design. Complex designs leading to infeasible manufacturing. You could have a designer that all the designer has done is CAD modeling in his brain, in his head. The question is, can I even make the design? And that brings me back to this point I was making, where we want to make sure the CAD designers are working closely with manufacturing team, they're closely working with materials team, and testing and analysis and non-destructive evaluation to make sure that whatever designs are being proposed can be achievable. And the designers have to be respectful to the stress engineers. And the stress engineers have to be respectful to the material scientists. Everybody has to respect each other. And sometimes these design organizations, that's not happening. And when that doesn't happen, and when the team is working not very oiled together, then you're going to have these issues. What happens if you're working towards a set of requirements and the requirements are changing on you? For example, I told you design this structure to 100 degrees Fahrenheit. but later I told you, hey, you know, sorry, we cannot go above 90 degrees F, then that's a change in requirements that could happen late in the game which could cause the whole thing to slip. So that's why requirements, functional requirements, and governing requirements that regulate the structure need to be communicated early in the process so it can be prepared for what's coming. The lack of engineering standards between the contractors and their suppliers. That can also cause then the suppliers to create products for the prime contractor that may not meet their own requirements or the requirements for the governing agency like FAA or NASA or whatever we're looking at here. There's also the lack of realistic cost estimates and this idea of the faster, better, and cheaper is always better, not necessarily. Faster, better, and cheaper could cause people to cut corners and not do the right things, such as getting material properties. We'll talk about that later. You know, getting the material properties that you need for your design so they can then design it in the first place instead of making them up. You know, so cutting those corners can also be an issue. So you may have a systems engineering in place, but you may not have the best systems engineering in place that could then cause an issue in the designs. You know, you can design the best structure in the world, but can you manufacture it? Are you using the right materials? Can you even test it? What if you design it and it doesn't meet any of these other requirements from propulsion, thermal, and anybody else? So I think the point I'm trying to make is that you ought to work with a team of engineers. You ought to work with a team of engineers. Otherwise, we're going to have some serious issues under consideration. That's a great point and great question. So what it takes to be a good systems engineering is to actually take training in that area, number one. So you want to take courses in that area. But number two, a good systems engineer is one that has experience doing it. So it has gone through various areas of expertise. The best systems engineers I've seen are ones that have actually worked all the systems. And then when they go back to systems engineering, they have all the knowledge from different disciplines. So they know the roadblocks to overcome. So in other words, a good systems engineer is one that has experience in multiple facets of the program and each discipline. So when they're in that position, they know what roadblocks will be encountered. It makes sense. You need to be a generalist. You need to know how to do a little bit of everything. And even schooling may not give you everything you need for that. You may want to get some experience when you work at a particular company and you tell management, hey, I want to work on systems engineering. Help me rotate around, right? Help me. If you don't be good systems engineering when you are hired, you want to get training, but you also want to get good at everything. You also want to get experience in all the different areas that you can, so that when you're working in systems engineering, you can be a generalist and you can identify those roadblocks when they show up, and you can help teams work well together. And that's hard to do when you don't understand what each team is really doing. The key ingredients for successful systems engineering is documentation, bringing the requirements down to the lowest level. So flowing down those requirements, functional requirements, and regulatory requirements all the way down. All the materials are going to be used, and making sure everybody understands what the materials are being talked about. The CAD drawings, having a very good configuration management of these CAD drawings, safety documents, interface controls, the interface controls between components, You also want to identify design drivers, the cost, schedule, and performance. To get high performance, reliability, and confidence, it is important to really consider the knowns and the uncertainties. Developing requirements, identifying options, doing analysis and trade studies, and defining product details. You also need to understand the acquisition strategies. And for the interface controls here that we're talking about what are the structural connections, the harness and connectors, software protocols, and signal processing. And then you also have to gain a fundamental understanding on project planning and budgets. So systems engineering disciplines applied through the project life cycle as a comprehensive, iterative technical and management process to ensure that you have a proper flow down of requirements. You can translate an operational need into a solution through a systematic concurrent approach to integrated design. So you want to make sure that the team is working well together. That's really what concurrent is really saying here, is you're working towards an end goal together. You want to integrate the technical input of the entire discipline team, the entire community, and all technical disciplines together. There needs to be a lot of communication between disciplines, ensuring that all compatibility of all interfaces, that all interfaces are compatible. You want to ensure that we consider the integration, verification, and validation of the processes through the life cycle, starting from the concept design. We also want to identify, characterize, and mitigate risks, and provide information for management decisions. And so here I have three legs at top level. The first one is systems design processes. The second one is technical management processes. And the third one is product realization processes. In the systems design processes, what we're really looking at there are four pillars in the systems design process. And they're used to define to baseline expectations, generate and baseline technical requirements, and then take those requirements and decompose them into logical models and provide them to the teams and convert them to technical requirements that the team can use to satisfy those baseline expectations. That's the bottom line, okay? And without that, we can't have a good systems engineering. If I don't have a good flow down of requirements, I don't have a good technical management process, I don't have a good way of talking about product realization processes, then we're going to have an issue to the point that I cannot realize a product in the first place. And they are established AS91 requirements for systems engineering that can help provide some structure to these systems engineering processes, to these 17 systems engineering processes, okay? So regulation, safety, environments, cost, schedule, and objective. We need to really understand what is the objective. Am I developing an aircraft for commercial applications, military, cargo? Who are the key players? Who are the stakeholders for the particular objective I have in mind? Is this aircraft going to just go from here to San Diego? Or is it going to go from here to Africa or another country? If it's a fighter jet, it needs to be extremely responsive. But if it's a fighter jet for military applications, the regulations for that may be different than if it's a commercial application. You also need to understand the regulations in the first place and need to understand what are the agencies involved. For example, the Federal Aviation Administration is the airworthiness authority here in America, United States of America. Well, the European one is the European Aviation Safety Agency. So there's various organizations. Or if I have a launch vehicle design, the launch vehicle design is for NASA. Well, it needs to meet some NASA requirements and so forth. Cost and schedule, again, we touched on that, but the point I want to make here that comes up a lot, and I will be covering more in this course, is skimping on important materials testing and not paying attention to that. Because if you do not put attention into materials testing, it can come to bite you later in the program, where that testing could have been valuable and could have basically expose issues early in the program rather than when it's too late. Maybe the failure happens during the testing of the full-scale article, an airplane, and then later on it's just too late to be able to accommodate any redesigns. And if you were to redesign, may as well just cancel the program. So it's very important to understand this and the consequences of not balancing cost and schedule with technical considerations. We also have the environments, the launch environments, the aircraft environments. We also have to make sure that the design goals are clear, lighter, cost, fuel efficient, quieter, and while also producing fewer carbon emissions. So the selection of the materials and the unique designs will allow you for addressing this concern. Safety is another one, and it affects elements such as manufacturing flaws, errors, human errors, natural hazards, impact events. These are things that need to be considered in the aircraft design. So milestones become the quite a bit of importance. They play quite a bit of importance in systems engineering. It basically allows you to check the system health as a function of time, from early opportunity to release, early concept design, and all the way down to the launch events or aircraft deployment or aircraft deployments to the different airliners. So these intermediate steps become a key role in determining how the project is going. You have several cycles that could be iterative at times. You have the initial research, the concept studies, you have the concept and technology development, and some of these could have a lower maturity readiness level in terms of technology. And then you can now start entering, once you have the concept design in place and you've gone through some mission concept reviews. And I'll be covering some of these MCRs, SRs, SDR, PDR, CDR, PCR. I'll be covering that in the next slide. But once you have the mission concept review, and I'll cover that in the next slide, and you've maturing the technology and the project cycle is maturing, right? You're maturing that design. You can then start fabricating and designing, and then you can assemble, test, and then you build to then either have to redo some aspects of this if there's a failure, but generally you're coming here down the road by going to an operational phase, where you're going to have to start tracking issues with the hardware. They're basically, most of them are human errors or non-conformances from not being able to build everything as you had expected. There's no way they can put a drawing out of a design and expect that everything's going to be perfect. That's not going to happen. And so you're going to have to address that during the delivery phase. And you're going to have to say, well, the aircraft thickness was supposed to be 0.12 inches, but when I made it and I'm testing it, it's not quite 0.12 inches. It's more like 0.08 inches. Well, you may have to revisit the test, or you may have to then assess whether, during the delivery phase, whether the customer will be okay with that delivery, which you know, with that big of a difference for the skin thickness of the aircraft, I'd rather go back and make sure I have everything well designed and manufactured properly. So there are technical reviews as you go through this life cycle process. And these technical reviews, MCR, SRR, SDR, PDR, CDR, and PCR are the ones I want to talk about now. So you have the kickoff meeting here typically where the team is provided some expectations about what the project is about. You know, you're gathering the subject matter expertise. You're trying to make sure you have the right expertise in the room. And then you have the mission concept review where the team discusses and outlines the project motivations and descriptions and merits. In here is where you're starting to talk about the concept designs. And in the midst of this phase here, phase A, you conduct a systems requirement review and a systems definition review. And here you outline the project's mission and vision. You determine the project structure. You communicate the project plan. You review the hardware, the software. You define and allocate all systems requirements. You determine that the approach that's going to be proposed is feasible and responsive to the requirements. And then you identify significant developments of or safety risks and their mitigation strategies. You also identify resources and define steps in the systems validation. Once you're gone through this process and your concept designs are likely to pass these functional requirements and these requirements that were defined through these two reviews, then you are readier to go to the PDR. And the PDR, you're looking at a preliminary design review where the team is getting closer to, hasn't finalized the design, but the conceptual design have been further matured. You have down selected the designs and you verify updates to the documents, plans, costs, schedule, risks that are involved with the design you're proposing. Perhaps you have an additive manufacturing material that is not looking that great. So that's a red risk right there. Perhaps you have a bolt design, a joint design that's is looking good. You can call that a green risk. It's not a risk at all. You want to describe the systems and its operations. You want to be able to determine the hardware and software specifications, drawings, verifications, and validation plans for the design, and reports any design analysis and engineering development results. So here is an important milestone that can be used to determine the health of how the design is going. Then we have the critical design review. Here, if you pass a PDR and you have addressed all the action items and you have addressed the risks that are coming up, you're closer now to start talking about what is going on with the structures that were designed. You know, how close are we to getting it out? We have the final documentation basically at this point. The margins of safety of the system have been defined and they have been discussed. The risks of the system have been mitigated for the most part. Some of the open items may be addressed later during testing. But this is a significant milestone that allows the release of engineering drawings. And so it's important that the designs are mature to the point there's high confidence they're likely to pass the testing that's going to be done later. Remember, at this point, you may not have done testing, although in some cases you may have had some testing done and some even heritage testing done. But at this point in time, you have some confidence through analysis with sufficient factors of safety that you are going to succeed. There are some great possibilities there that you'll succeed. The review will include examination of engineering specialty, risk management plans, allotted costs, and schedules. And the team is going to provide a complete design, manufacturing, assembly plans. They're going to tell you how everything gets transported, what kind of testing is planned. You may, you're going to review this and make sure that you can actually even manufacture it. So the CDR is a major review in all systems. Then you have the process checkpoint review. It's a checkpoint to make sure that we are on track for delivering the product, and that the team will test the quality of the system and include all the lessons learned. You also, at this point, are developing operational manuals and maintenance manuals, and verify and validate the systems and subsystems. Because if there's an issue and you have to redesign, you may have to go back a little bit in this life cycle process. Systems engineering, like I said, provides a standardized approach. Here is what we call the V. And this V, it superimposes the major milestone. Mission, basically you have the mission concept review, which is MCR. Then you have the systems requirements review, which is SRR, and so forth. Here we're outlining that superimposed with the V, the systems engineering V, validation and verification. The concept of operation, the high level requirements, the detailed requirements, the detailed design. So have we designed the right aircraft? Are the requirements right? That's what you're asking here. And as I move on to the later part of the V, I'm looking at implementation now. I'm looking at integration and test. I'm looking at subsystem verification. I'm looking at system verification. I'm looking at operation and maintenance. As I move up the V, the question now turns from have I designed the right aircraft to have I built the right aircraft? And have I met those requirements? Here I'm saying, are those the right requirements? Here is, have I met those requirements? And so it's a big turn of events here, as you can see, okay? And so this V provides a simultaneous product and process development, as well as a common basis for communications, and ensures that correct technical tasks get done during development through planning, tracking, and coordination. Here, I'm always going back and asking those questions again. I'm always going back and checking. Does it make sense? Did my original assumptions make sense? Am I building the right aircraft? You know, you're asking those questions even when you're going up the V, because what if you mess up? You may have to go back and revisit these requirements, and you may have to revisit, am I really designing what I wanted to in the first place? Okay. You can see here the cumulative percentage life cycle cost against time. This has been adopted by this report here. And you can see here that you are spending a great deal of time here in the product test side, and then you're going to spend a lot of time later on doing operations. And the cost is typically increasing over time as well, okay? And the cost to change direction later on becomes more and more difficult. So if I'm further down in the design process, and I find that I have to change something, then that's going to cost a lot of money. I have to go back and redo a lot of stuff. And that's why it's important to do as many material tests as you can and subcomponent level testing as you can at the beginning to inform the design, inform the developments, so that when you're in this phase, any change in direction is minimal in terms of cost and schedule. But once you step into production and testing and you have some major issues, you're looking at 500 times increase in cost, and that's going to be a significant problem for you, for the product. The Boeing process can be summarized in 3 different flow charts. You have a continuous feedback of information going back and forth between design requirements, regulatory requirements. So design requirements are different from regulatory requirements. And these things fed into the design. And we need to then validate and certify those designs so that I can then certify to enter it into service. But through this process, I have continuous feedback of information. I also have to keep in mind that as a systems engineering comes into play, that there's three areas that have to work very well together: manufacturers, the airworthiness authorities, and the operators. And all these three things have to work together. These three areas have to work together. Otherwise, you may have a design it doesn't work well. It may not meet the regulations. It may not be easy to inspect. It may be difficult to maintain, and so forth. And so in all this, I want to go one layer deeper. We have the structure's design criteria. Can I make the part? Is it crash worthy? Does it meet, is it damage tolerant? If I have a flock, will it stop? Will it arrest? Does it have enough durability? Can it take impact damage, for example? Is the stiffness correct? Do you have good fastener designs? Are the design loads adequate? Have I looked at all the discrete events? Can I maintain the structure that's been designed? All these three flow charts need to be taken into account, and Boeing did a good job of putting this together, and that's the one paper I discussed earlier that you should go ahead and read. And so here, when I look at a bigger flow chart now, that includes disciplines, for example, it has the same elements that we talked about, but I think it's good to see them. I think it's good to see them in this context. You have requirements and specifications. You have performance and weight cost trade-off studies. And here you're in conceptual design and you're looking at candidate configurations. You select the right configuration layouts. And here you're looking at analyses that's going to be multidisciplinary. You're going to have aerodynamics, propulsion, the mass properties team, the loads, the structural sizing, the air mechanics, and can you even make the part, and the avionics. All that has to come together, and this is typically true for launch vehicles, aircraft, and spacecraft. Once you go there, you go into preliminary design, and again, all disciplines are involved, and wind tunnel models become important to demonstrate that those loads are presumed are even accurate. And then you enter into a phase where you start finalizing those designs and you enter into production, because you're going to have to test those designs to make sure they work. And again, that requires engineering laboratories. It may include integrated disciplines together, working together to determine whether the production design is adequate. And here you have laid out the designs. After CDR, you can release the drawings to then start manufacturing the parts. And that's going to require facility developments, tool designs, fabrications, assembly. And here you have quality assurance getting involved and making sure that the parts are getting fabricated to high standards. And once you've gone through flight testing and the product has been certified, it's time to deliver the aircraft, and along with ensuring the whole time as you're working through these drawings that you are developing manuals for maintenance and structural repair manuals. This process is going to require some preliminary sizing. A lot of questions I get sometimes is, can I start using finite element models early in the design process, the conceptual design phase? But the fact of the matter is that most airframe structures are highly redundant structures, and space vehicles like launch vehicles and spacecraft have little redundancy. Regardless, typically when you're in the concept design phase and preliminary design, you try to rely on hand calculations that verify for simple finite element modeling. And so for simple members, it could be a simple analysis that's done with hand calculations and using a calculator like Excel or something like that. You can approximate some of the designs. You can apply simple stress methods that you learn from mechanics and materials rather than a detailed analysis, because detailed finite element modeling is highly cost it's not cost effective, and it's not going to, it may not put you in the ballpark as quick as a preliminary analysis. So the preliminary structural sizing input data are required for several analysis cycles, and it could include finite elements. It's just that before you touch finite elements, you want to ensure that you have done some preliminary sizing by hand calculations. Because once you go to the detailed sizing, that takes a lot of time, especially when finite elements are used. Sometimes detailed sizing is very difficult to do by hand calculation. Hand calculation puts you in the ballpark, but then the detailed work puts you closer to the goals that you need to achieve, because finite elements, already required. You're looking at structural designs that have very low factors of safety, that have to be weight sensitive, basically low weight, and cost effective. And so you want to make sure that you've done as much sizing as possible by hand calculation before you step into more complicated modeling. And bottom line, is the design adequate? To answer that question, there's cycles that you have to go through. Initial design concept, you have to ask the question, do I have positive margins? Initial design, do I have positive margins? I do a stress analysis, figure that out, and I iterate with the design and then go into more detailed design until I'm happy with the final design. Now, that doesn't mean that the structure is going to be safe. I have to test the structure first and validate my models, because if there's a problem there, then I may have to go back to the drawing board, and that, as we said, will cost quite a bit of money. The more time passes by and the more mature the system becomes, if I have to change direction, we're looking at a significant amount of cost and schedule delays. Systems engineering, launch vehicle and space vehicles is extremely important and is required. Contractors on either side are different, so the contractor for launch vehicle may be different from the contractor in a space vehicle. And also, these vehicles have to be coupled together in the dynamic models. We'll be talking about that. And so systems engineering here is highly required. The interfaces from the launch vehicle side need to be properly defined compared to the space vehicle side. The vibration environments that launch vehicle produces, you don't want to break the space vehicle with those vibrations during ascent. So all of that shows and highlights the importance of systems engineering. What if I need a 90,000 pound payload? Is the launch vehicle I'm selecting even able to take that? I'm going to show an example of a user's manual that provides essential data on the Orion 5 launch system, which together with their other launch systems constitutes their transportation systems. And so their user's manual typically contains compatibility of a spacecraft and spacecraft mission with launch system. It constitutes the general launch service provisions and specifications, and provides data to initiate and prepare of all technical and operational requirements for any launch of any spacecraft on the launch vehicle. So again, you have the payload inside the launch vehicle. We want to make sure that we have compatible systems. And so here's a Orion 5 Users Manual, issue 5, revision 2 is an older version, but the bottom line here is that it gives you information about the various systems from the payload fairing. The diameter is 5.4 meters. What if you have a bigger payload? Maybe you have to come up with a different fairing. What kind of acoustic protection you have for your spacecraft. It's going to give you information about the adapters. And the launch vehicle adapters they're going to connect to your spacecraft. It will give you information on the upper stage and the attitude control powered phase. It's going to give you information about combustion time and so forth. It's going to give you information about the main core stage and the star rocket booster, ISP information, combustion time, the engines, ISP. What kind of structure are we talking about? Stainless steel case in their case. And it's going to give you information about avionics, as you can see in all the different components. Here is a quick view of the kinds of information you will find in their user's manual. It's going to provide information on the performance and launch mission, what kind of orbits you can achieve, insertion accuracies, mission duration, launch windows. It's going to give you information about spacecraft orientation during ascent phase. Horizontal, vertical, how is it oriented? Separation conditions. It's going to have information on the environments, static acceleration, steady state angular motion. It's going to give you all the information you need to be able to ensure your spacecraft can sustain those environments. Thermal environments. How clean is the system for the spacecraft, and the electromagnetic environments, and the RF system, and the ranges, and does it overlap with the spacecraft? You also have the spacecraft design and the requirements for those, and what is compatible. Spacecraft interfaces, where are those interfaces defined, and how they're encapsulating the spacecraft interfaces, and so forth. So you're going to see a lot of information there on that. And then you have the operational space center location, and the range information and mission control information, so forth. You also have mission integration and management, the launch campaign itself, countdown information, spacecraft operation plans, quality assurance, and then you also have a bunch of appendices normally that provide even additional information there. So I hope that makes sense to you guys as we go through. So what are the keys to success in any program? In any program, to succeed, it's important that we have effective communication across the organizations, the design authority, the end customers. We want to have a great communication across the same company as well. It's important to use a building block approach. We'll be talking about that more, but it's important to characterize the material properties and build confidence in the analysis via testing. We also want to evaluate the basic design through testing, manage uncertainty, and we'll go through all of that into a deeper level later. You also want to make sure that as built hardware is good for the actual application. So if the thickness of the fuselage came out shorter than the thinner than the actual drawings, you will not be able to evaluate that, the workmanship of it. And one of the most important things is to apply lessons learned from past failures and anomaly. One of the biggest lessons learned I want you to keep in mind as we go through this course is to not to forget the lesson learned. That is a lesson learned, not to forget the lesson learned, from past failures and anomalies and bring them to light as you're working through issues. If there's a corrosion issue with the particular material system, or there's a hydrogen embrittlement situation, or some other scenario, failure mode of concern, you want to bring those elements in into the design to make sure you're not repeating those mistakes. So communication allows building an understanding up front, ensure the set of requirements is complete, and provide upfront understanding of structural requirements and the rationale behind them. You also want to integrate the oversight, design authority, and customer teams early to flush out best practices relative to test, analysis, and workmanship of structures. I think it's important to have face-to-face meetings to build healthy professional relationships and to demonstrate a mutual interest in ensuring that you're marching towards the same goals as everybody else, because you don't want to have miscommunication too late in the game. And while requirements imposed by the regulatory agencies like NASA are gold standard, it is important for the teams to be open-minded about possible ways to solving the issues at stake. There might be ways to get there that have a low level of risk compared to other alternate options provided, or the one path that is being used. So it is important to form, as a systems engineer, a collaborative environment that facilitates communication, data transmittals, resolution of concerns, and promotes the identification of technical solutions. So in summary, the point I want to make is that systems engineering is key to having a successful project. And that if I were just to teach structural engineering when it applies to aerospace structures, I am missing the point. And I'm missing the point because to have a successful aerospace structure, I have to be successful in having the various disciplines talk to each other. I want to have the CAD model that a designer put together. I want to make sure that's manufacturable. I want to make sure that it's testable. I want to make sure it's inspectable. I want to make sure that the designer and the analyst are working well together so that the power trip that one of them may have, because maybe one of them has a PhD or one of them has more training, that power trip is put secondary. Because the minute the egos go up, your products will take a suffering. So it's important that the teams work well together. It's important that teams be humble across each other, and then the systems engineer is able to smooth out any relationships and making sure the flow down of requirements, interface requirements, regulatory requirements, functional and performance requirements, that all these are working well together. And then all that is put together and monitored to a series of milestones across the program as we march forward.